In this video, we're going to take a look at what it means for a function to be differentiable. Right? So we would say that a function is differentiable at x equals c for a function f of x if the derivative at c exists. So it's pretty intuitive. We would say that a function is differentiable somewhere if you can take its derivative there, or in other words, if it has a slope there. Now let's break down what that means exactly. Right, if we had a function like x squared, right, we look at the graph of x squared right here, and we know just from our derivative rules that we can take its derivative. So our derivative is 2x, and 2x is very, very nice. Any x value I wanted to plug in, I would get an answer. So is x squared differentiable at 3? Yes, it is. How do I know that? Because I can take the derivative and plug in 3, and I know that the slope right here is 6, right? That's 2 times 3. So it's differentiable at 3, and for the same reasons, it's differentiable at 4 and 5 and 100 and every x value. So x squared is differentiable everywhere. So if that happens, normally what we say is we say that the function is a differentiable function. We don't even specify really individual points. If it's differentiable everywhere, we would just say that x squared is differentiable, period. We can take its derivative. Now, let's look at what this means in like a graphical sense, because this is also important. All right, if we have our graph of x squared, hopefully you remember the limit definition of a derivative. So where do derivatives come from? Don't think that they just come from the shortcut rules. They previously came, or it was originally defined in terms of a limit, right? Where you take 2 points here, and we take the limit of x plus h minus f of x all over h, between a point x and then a secondary point over here to the side, and then we let that h get smaller and smaller and smaller, which transforms the secant line into whatever the tangent line would look like. So if we take a look right here, if we picked some given distance h right here, this guy would have a slope that's positive, but as the h gets smaller, look at each of these successive tangent lines. Do you see how they get flatter and flatter and flatter? And they converge, right? They converge to be a flat line with a slope of 0, right? As the derivative would tell us. And on the other side, remember, limits have to be taken from both directions. As h approaches 0, when h is negative, or on the left-hand side of 0, they would go in precisely the other order. So we have these slopes, some positive and some negative, but as you get closer to the origin, the slopes converge to 0, and so the limit exists, right? That's the angle I want to come at this from. The limit exists because it's the same from both sides, and so since the limit exists, that means that the derivative exists. And so is it differentiable at 0? Well, yes, it is. Well, what I'm trying to get at, the kind of the behind the scenes picture I'm trying to paint here, is this idea of smoothness. When you're talking about a function being differentiable, a function will be smooth, right? So if it's smooth like a parabola, that's really the equivalent of being differentiable, because any point that you pick, as you take these successive secant lines, as the h goes to 0, the limit from the left will match the limit from the right only if the function is smooth. If there's an abrupt change, or there's really two scenarios, either a corner which would be a sharp edge, or something called a cusp. A cusp happens for some functions with rational exponents. Corners look like this, cusps look like this, and you see how in both of these cases that's not smooth. So functions would not be differentiable if they had corners like this. Let me show you what I'm talking about. Here's an example. A function we know very well, the absolute value graph. If you noticed, whenever we talked about the derivative rules, did we ever discuss an absolute value rule? I don't think we did. We covered power rule, product rule, quotient rule, chain rule, but we never learned how to differentiate an absolute value function. Here's why. It's not a differentiable function. There is no derivative for the absolute value function. Now, how come? Well, it's because it has a sharp corner, right? It's not smooth, so it's not a differentiable function. Now, does that mean that we can't take the derivative anywhere? Not exactly. For instance, let's look here. If we just restrict our attention to the x's past 0, well, we're past the corner here, and the slope anywhere after 0 looks like it's a consistent slope of 1, doesn't it? Right? 45 degrees, up 1 over 1, up 1 over 1. It looks basically like the graph y equals x if the if the x values are past 0, because the absolute value of x would just be x if the x's were past 0. Right? Likewise, if the x's are less than 0 for before the origin, looks like the slopes are always negative 1. Right? Negative 1 before the origin. But at 0, the limit would not exist from the left and the right if you were doing the limit of this difference quotient right here. The slopes from the left are always negative 1. Slopes from the right are always positive 1. So this would be does not exist. The derivative doesn't exist at the origin. And again, it's because there's a sharp corner. If we look at it in this graphical sense, it still makes sense, hopefully, as I was explaining before. If we highlight the origin as 1 point, and then we pick any h value that's positive, as the h gets smaller and smaller and smaller, this slope will always be 1. It's never 1 and then works its way towards 0, like 0.9, 0.8, 0.7 on its way down to 0. It's always 1. Even if you were a millimeter away from the origin, rise over run between the origin and that point would be 1 still. Likewise, even if you were a millimeter to the left of the origin, the slope of this line would still be negative 1. So those limits would not meet. If you were to draw the slopes from either direction, it would be 1 from the right and negative 1 from the left, and no derivative at all in the middle. So because it's not differentiable everywhere, we say that the absolute value function is not a differentiable function. All right, now, let's tie this connection between differentiability, right, being able to take a derivative, and being continuous. Let's think about this for a minute. I'm going to ask you a question, and you can pause the video to think about it if you need to. If a function's differentiable, does that imply that it's also continuous? Or if a function's continuous, does that mean that it has to be differentiable? So how should I draw these arrows here? Or is it both ways or neither way? Or what's the connection here? So pause the video if you need to, but I'm going to go ahead and tell you right now. First of all, if a function's continuous, that does not mean that it has to be differentiable. What's an example? How about the one we just looked at? The absolute value graph is continuous. You can draw it without picking up your pencil, but because of the sharp corners, right? It might not be differentiable. Now, what if it's differentiable? Does that mean that it has to be continuous? Yeah, differentiability is a stronger condition than being continuous. So this direction is true. If it's differentiable, your function has to be continuous for sure. Right? If that limit's going to exist of the difference quotient, has to be not only continuous, but also smooth as well.